Thank you very much. So hello everyone, I'm Aurora Rossi, and today I will talk about the package GraphNeuralNetworks.jl. So let me introduce myself. So I am a third-year PhD student at Université Côte d'Azur, and as Avik said, I participated to 2 summers of code, working on the library, in particular on the temporal graph aspect, and with the Google summer of code and Julia summer of code. And in October, I will start a postdoc at the University of Bonn. So the content of today's talk are an introduction to the library. I will describe you the basic graph data structure we support. I will show you the message passing procedure. I will tell you the definition of graph neural network, some convolution that we have in the library, and how to create a new custom convolution. Then I will show you an example of a simple training code, and the graph dataset we can import from the ML dataset.jl package. Then I will describe the future plans of the package that we have for the package, and I will show a simple notebook about the Karate Club example. So let's start with the package. So it's an open source Julia multi-package that is designed to create and build, train graph neural networks. It was created by Carlo Lucibello and is inspired by Python geometrics, for example. And we recently published a paper on Journal of Machine Learning Research describing this package. And so I say that is a multi-package. In fact, it contains four main packages. So the first one is GraphNeuralNetworks.jl that contains the stateful graph convolution. So it's based on the framework Flux.jl. Then we have GNN-Lux.jl that contains the stateless graph neural networks, and it's based on the Lux.jl framework. And then we have, so these 2 packages are meant for user. Instead, the other 2 are built-in function. So we have GNN-lib.jl that contains the implementation of basic message passing function and the functional implementation of graph convolutional layers. And then we have GNN-graph.jl that contains the graph data structure and the helper function. And this package depends mainly on graph.jl. And so you can see the 4 main dependencies that are Flux, Lux, graph.jl, and nnlib.jl. So now we move on with the graph data structures. So I want to recall you what is a graph. So a graph is a data structure where V is the set of nodes and E is the set of edges, where the edges are pair of nodes. And in machine learning, we can add some additional information at the level of the nodes, at the level of the edges, and at the level of the whole graph. And this additional information are called features, and usually are represented, for example, by arrays. And there are several ways to create a graph in our library, and the standard type is the GNN graph, which are always represented as directed graph. And here we can, for example, create a random graph with 10 nodes and 60 edges. Then we can add the feature at the level of the node, edge, and at the level of the graph. And you can see that the first dimension is the dimension of the feature, and the second dimension is the dimension, so the number of nodes, edge, and the number of graphs. So, for example, here we have just 1 graph. And here is the summary of the structure. Then we can create a graph starting from the adjacency matrix, for example, or the adjacency list in this way. And the last representation from which we can create a GNN graph is the CO representation. So we have two arrays that contains the source node of the edges and the target nodes. So for example, the first entry of source means that we are looking at the edge from 1 to 2, and the source node of this edge is 1. And then we have the target that is 2, because this edge goes in this way. And so this is another way to create a GNN graph. Then we support also heterogeneous graph, which are graphs with different types of node and relationship and edges. And for example, an example of a heterogeneous graph is a graph in which we have users and movies, and a user can like and dislike movies. And so you can create a GNN heterograph in this way, where you can define which are the relations, so the node from which they start, the kind of relation, and the movie. So, and the other node. And then here we give the edges as a CO representation. And then you also can manipulate this kind of structure. For example, you can add edges, and in this way you can add an edge that goes from node 2 to node 1. And also in this case, you can add data feature. And for example, if you want to add data feature at the level of node user, for example, you can add the age, and so you can do it in this way. Or you can do for the movie, and you can add the information about the release year. And again, here there is the summary of the graph, GNN heterograph. For the temporal graph, so temporal graph can model different situations in which we take in account the temporality, the time, and we can divide temporal graph in two cases. The first one is static temporal graph, that are graph in which the graph structure is fixed. So the topology is fixed, while the feature change over time. And in this case, we can implement this using the GNN graph type that I described to you before. And after, we can also create a dynamic temporal graph, which means that both the graph topology and the feature change over time. In this case, we handle just the case in which the number of nodes are fixed and the edges instead can change over time. And in this case, the temporal graph can be seen as a collection of static graph, and so it is called a temporal snapshot GNN graph type. And also, in this case, we can create some snapshots. So, two, for example, a static graph. And then we can create a temporal graph and add the feature and also a label for the whole temporal graph. And here there is the summary of the graph. And then you can also access to the node data directly from the temporal graph. Now we pass to the message passing concept. So for those of you that are not familiar with the graph neural network, I will describe briefly the message passing procedure and the graph neural network definition. So the message passing is a procedure that can be divided in 3 steps. The first one is the computation of a message from the neighbor of a node. Then there is the aggregation of all these messages and the update of the current feature of the node. So in order to understand better these passages, let's look at it from the point of view of node 3. And so node 3 has 2 neighbors, and we can compute the messages from them. So we can compute 2 messages with a message function. And after that, with a permutation invariant function, we can aggregate the 2 messages. And after that, we obtain an aggregated message that we use to update the current information of node 3 with another function that is called update function. And this procedure is done in parallel for every node. We implement the message passing procedure using the propagate function, and it is divided in other two subfunctions that relies on the gather and scatter function that I will describe in a minute. But first, let's see the propagate function. So we can give to it the message function. So in this case, we just add +1 to every message. And then the aggregation function is the sum. And so we obtain for each node, the value is basically the double of the degree of the node. In this simple case. And let's see how to create this using gather and scatter. So this is a very simple graph in which we have as a feature some scalar, 5, 6, 7, and 8. And so we can create the messages using gather, and the first input vector are the feature of the node, and then the second are the source of our co-representation. And then we create our message function. As before, I just put +1 for simplicity. We apply the message to every message that we collected, and then the updated messages can be produced with the scatter function that takes the messages, and then they are mapped to these indices, so this destination that are the target of the co-representation. And so, for example, 6 in the first that is the first message will go in node 3, and so we will see it here. And then we repeat the procedure, so the second message will go to the fourth node, and as the 7 and 8, so we obtain 21 because we have the sum function that put together with the sum all the messages that go in the same node. And then we have 9, that is the last one, that go in the node 1, so we see it here. And there are no information that go to node 2, and so it's 0. Okay, so now we are ready to define what is a graph neural network. So a graph neural network is the message passing procedure in which the update and the message function are learnable function, and in this case are neural networks. And as every machine learning architecture that can be trained, in the case of supervising training, you have to it is an optimization problem in which you have to minimize a loss function, but probably all of you are familiar with this concept. And so what are the tasks that GNN can perform? There are several tasks, but we can group them in 3 main classes. So the first one is the graph classification, link prediction, and node classification. So graph classification is the problem of determining the category of the graph. So after performing some message passing layer, we have some updated feature that we want to group together. So we sum all of them together with the pooling operation, and we obtain only one array that is called graph embedding. And this is the input of a multi-layer perceptron that will classify our graph. Similarly, we can do the node classification, so we want to determine the category of a node. We perform some message passing layer, and after that, we want to understand the category, for example, of node 6. So we take his feature, we use it as the input of multi-layer perceptron, and again it will give us the class of the node. And the link prediction instead is the problem of determining whether there will be an edge between 2 nodes. So after performing some message passing layer, we can choose 2 nodes that we want to understand if they will be connected or not. So as before, we give the feature as input of a multi-layer perceptron that will give the answer yes or no. Okay, so in our library, we have a list of graph convolution that are already implemented. So you can, and we support, for example, the graph isomorphism convolution or the graph attention convolution, some of the most famous convolution. But of course, you can also customize, create your own graph convolution. And to do that, you have to create a struct in which you put all the weight and parameters of your convolution, of your layer. And then you create a constructor in which you initialize the parameters and the weight. And after that, you have to create the forward function that will apply the graph convolution. And you can create layers, but you also can create model. So, for example, here you can create a model that has two convolution and a dense, so a classifier. As before, you create the constructor and then the forward pass. In this case, the example is with Flux, but similarly, you can create it in the Lux ecosystem. So here, there is a training example in which we create some synthetic data. We create the training set. We create a model using GNN chain that work similarly to the chain of Flux and Lux. So it is useful when you don't have to customize your model. You just use the chain with already built-in function and layers. Then you define the optimizer, the loss function, and then the training loop is very simple, very similar to the Flux and Lux ecosystem. We support the dataset that are contained in ML dataset.jl. There are all these graph dataset. So we support static, temporal, and heterogeneous dataset. Some of them are collection of dataset, like the TU dataset and the OBG dataset. So, future plan. We would like to optimize the message passing operation and improve this sparse metric operation on GPUs. And actually, this is a work in progress by Davide Ferré as a project of the Google Summer of Code this year. Then we would like to support additional hardware backends, such as the Apple Silicon Metal and TPUs. Because now we are supporting CUDA and AMD GPU. And we would like to also enabling multi-GPU training. So now we can move to a very simple example of the Karate Club network. So this is the QR that brings you to the notebook. And so if you click on the link, this is the notebook. So the Karate Club graph is a small graph that contains 34 nodes, and each node represents a person in the Karate Club. And we want to, so the dataset can be imported from the MLL dataset.jl package, and the task we want to perform is to classify the cluster of people that meet outside the Karate Club. And so we can find in the dataset the graph, but also the feature that are the label of the club, that is label for each person of the club and for each group outside the club. So the first person will go out with the people of group 1 and so on. Okay, so we can import the graph using this function that creates the GNN graph. And then, given the fact that in this case we have just one graph, the training will be using just a subset of nodes, and we will test to the other part of the graph. And to do that, we need a training mask that select which node are used in the training set and which are not in the training set. And then we, of course, create the on-batch labels, and we have the general graph. Okay, and then this is the graph of the people in the karate club and the communities that are outside the karate. And instead, this is the simple model that we use that has 3 convolution and 1 classifier. Okay. And then we can visualize the embedding before the training, and we can see that already we can see the communities that are quite near together. And then we use the logic cross entropy as lost. Then here, this is the training loop that I described before, and we can see that the loss function is decreasing. And then we have the, sorry, it's not, oh. We have that the training accuracy goes to 100, and the test accuracy is 80. And this is the final embedding. And we see that in this upper part are the blue nodes, and then on the other side there are the yellow node, the purple node, and the green node. Okay, and with that, I would like to thank you for your attention.
Thanks for the talk. So yesterday there was a talk by, I think it was yesterday, by James Fairbanks about AC sets. And in that talk, he talked about how a lot of graphs that have metadata can actually be represented as like higher level graphs like hypergraphs or multigraphs or other kinds of combinatorial data structures. And it looks like graph neural networks use a lot of graphs with metadata. So do you think any of those sorts of techniques would make sense to be applied to graph neural networks?
I'm not familiar with that kind of structure, but probably yes, there should be already some model that work with simple chal or complexes, something like that. Yeah.
Thanks. That's impressive. I'm curious. You mentioned that there's some famous packages that have been supported, like Sage, like graph attention networks. Where I assume simplified, just very simple graph convolution networks. I guess from a developer perspective, do you have a sense of what additional package, what additional model choices that you want to focus on next?
I focused on the temporal models. In fact, here there was not the list on the temporal part, but yeah, probably we would like to focus on the models that are the most used one and the newest one. So yeah,
cool. Thanks.
Thank you.
Thank you very much for your presentation. I learned a lot. So I'm not from the field, but I'm wondering, like, how do you compare your implementation against, what I could find in Python? Like, what would be really the selling point of your work against, what exists outside? So.
We did in Julia because was missing a package about graph neural network that was maintained, because there is a geometric flux, but we think that is a Y that is not anymore maintained. And so yeah, it's just mainly for the Julia user. And we think that also we have a lot of features that are missing with respect to the Python geometric library, because there are less people that are working on the Julia library. And we still have to do a benchmark, but we think that the performance should be the same because we are working on GPUs. So, yeah.
But maybe like in terms of, how, because somehow you have a domain-specific language to, to say what actually you want to do. So maybe this is where, it could be interesting to compare as well, not just in terms of performance, but also like how do you express a workload, how do you express some work, just an idea.
Okay. Thank you.
Hey, thank you so much for the talk. I had a couple questions. I was really impressed early on, also in the presentation, with regards to kind of the plethora of, I guess, graph neural network specific types that you had for different types of graphs. So you were mentioning like these temporal graph structures, things like that. I was just kind of curious, is there any interest in the work that you're pursuing to perhaps spin some of those types out into its own package? I'm just wondering, because some of my work would be really interested just using some of those structures, like temporal graph structures, monitoring that over time, tracking feature changes as time evolves. I was just very curious if you're thinking about keeping that consolidated within kind of the stack that you're presenting at the very beginning, or if you're thinking about maybe spinning it out into other, like maybe graphs compatible, like graphs.jl compatible packages, or what are you thinking?
Yeah, at the moment we are keeping everything in that package. We recently split the package in Graph Neural Network and GNN LAX just to handle the true machine learning ecosystem. But at the moment we are keeping this format. Yeah.
Okay, thank you so much.
You. Yeah, and one thing that I didn't mention before is that with respect to Python geometric, for the temporal graph part, we are at the same level, basically, yeah. Because there is the Python geometric temporal package, but that one seems not to be maintained, and they are trying to put in Python geometric the temporal graph, but I'm not sure if they are at the same level of us. Yeah.
No, this just seemed very advanced. That's why I was wondering. Okay.
Thank you.
I have one question. You mentioned that you're looking at supporting reactant for like different hardware backends. Have you done any experiments with that? And if you have, like, are there any shortcomings that you have faced?
No, I am not aware of the details about that. Yeah, thank you.
Okay, if there are no more questions, let's thank the speaker once more.
Thank you.